Welcome to Unit 7, Lesson 5, Related Rates. What are related rates problems? Related rates is really about solving word problems using chain rule and implicit differentiation. So, uh, it's a good idea to go review topics 5.1 and 5.2 in Google Classroom if you don't feel confident about these two topics. Here's an example. If b equals a squared plus 3a, a equals 4, dA over dt equals 2. What is the rate of change of b? So rate of change of b is really just dB over dt. So that's what we're looking for. Okay, so we know that b equals a squared plus 3a. We are going to differentiate both sides. So what we're really doing is we're doing this. d over dt of this side, and then d over dt of this side. Okay. So the derivative of b with respect to t, that's the derivative of b is 1, so it's 1 times dB over dt plus the derivative of a squared is 2a times dA over at because of chain rule. The derivative of 3a is 3 times dA over dt, also because of chain rule. Okay, what do we know? Well, first of all, we're looking for this one. We are looking for dB over dt. That's the unknown. That's right here. What do we do know? We know that a is 4. So that's 4. We know that dA over dt is 2. Okay, so we're just plugging in at this point. And when we plug in, when we plug in, we get dB over dt, which is what we want, is equal to 2 times 4 times 2 plus 3 times 2, which is 16 plus 6, which is 22. So we know that dB over dt is 22. Okay. So the general method for solving these questions, we can go here. First, we set up the equation. In the last problem, we're just given the equation. For word problems, we might have to figure out the equations ourselves. Differentiate both sides. Plug in what we know. Sometimes we have to solve for them. We'll see some examples, and then solve for the unknown. One more example where we're just given the equation. X squared plus 2y plus y squared equals 20. X equals 4. Y equals 3. dy over dt equals 12. We want x dx over dt. Okay. So our equation again, x squared plus 2y plus y squared equals 20. Okay. Differentiate both sides. So if we take the derivative of both sides with respect to time, the derivative of x squared is 2x times dx over dt. The derivative of 2y is 2 times dy over dt. The derivative of y squared is 2y times dy over dt. And the derivative of 20 is just 0, because 20 is a constant. So step 1, write down the equation. Step 2, take the derivative of both sides, which we just did. Step 3, we plug in what we know. We're looking for dx over dt. So let's see. We know x is right here. X is 4. So we have 2 times 4. We don't know dx over dt. We're looking for that. We know dy over dt. That is 12. Plus 2 times y. We know y is 3. Times dy over dt, that's also 12, equals 0. So 8 times dx over dt plus 24 plus 72 equals 0. So 8 times dx over dt equals negative 96. That means that dx over dt is negative 96 divided by 8, which is negative 12. That's it. Okay. Next, let's look at some word problems that are closer to real life. Here's a geometry example number 1. We have a rocket right here. The rocket rises vertically. Vertical means going up, down. So this rocket is going straight up. We're told that there's a camera here. So here's the camera. It's 5,000 feet away from the bottom right here. So the whole thing makes a right triangle. When the rocket is 1,000 feet above the launch pad, its velocity is 600 feet per second. Find the rate of change of the camera's angle as a function of time so that it stays focused on the rocket. Alright, so we have right triangle. We have an angle theta. The opposite is h. The adjacent is 5,000. So we can use tangent. So tangent of theta. So step 1 is to set up the equation. Tangent of theta has to equal h over 5,000. Okay. Step 2, take the derivative of both sides. All right, we can do that. The derivative of tangent theta is secant squared theta. And then because of chain rule, that's times d theta over dt. And then the derivative of h over 5,000 is 1 over 5,000 times dh over dt. Okay. Next, we plug in what we know. So we're looking for d theta over dt. We're looking for the rate of change of the camera's angle. So we're trying to find d theta over dt. So that one is okay if we don't know because we're solving for it. We're told that the rocket is moving up at 600 feet per second, so that has to be a dh over dt. That's 600. What is secant squared theta? Well, we know that if this is 5,000 and we know that this is 1,000, then by the Pythagorean theorem, c squared has to equal to c squared has to equal to 5,000 squared plus 1,000 squared. So c squared is 25,000,000 plus 1 followed by 6 zeros. So c squared is 26 followed by 6 zeros. Okay. Okay. Taking the square root of both sides, we can use a calculator. We want the square root of 26 million. Square root of 26 million gives us about 5,100. So this is about, therefore C is about 5,100. Well, if that's the case, that means that cosine of theta would be adjacent 5,000 over hypotenuse 5,100. So, which is equal to, let's actually simplify right now, might as well, which is equal to 50 over 51. Secant is the inverse of cosine, so secant theta is 51 over 50. Therefore, we can plug this in. This must be 51 over 50 square. Okay, let's go to Google. What's 51 over 50 squared? That is about 1.0404. So plugging these things in, we get 1, this is too thick, let's try this again. So it's going to be 1.0404 d theta over dt equals 600 over 1500. Okay, 600 over 1500 is 6 over 15, which is 3 over 5, which is 0.6. Sorry, it's 2 over 5, which is 0.4. Okay. Therefore, d theta over dt has to equal 0.4 divided by 1.0404. Okay, again, we can use a calculator. 0.4 divided by 1.0404. That's about 0.38. So d theta over dt is about 0.38. Okay. Okay. Sorry, I made a mistake here. Careless mistake. So this is 5,000, and I copied it down and turned it into 1,500. That's not the same thing. It's not 5,000. Well, it's not 1,500. It's actually 5,000. That should be 5, not 1,500. 5,000. Okay. So our final answer should be about 600 over 5,000 divided by 1.04 or so. Oops. Which gives us roughly 0.12, about 0.1. So d theta over t is about 0.1. Okay. All right. Example 2. Here we have a funnel. So this whole thing is called a funnel. Water comes down like this. Water is draining from a funnel at a rate of 0.02 cubic feet per second. The length right here of the funnel is 2. The radius is 1. The funnel is a cone, so that we know that the volume of a cone is 1/3 pi squared h. That's really just saying that the base is a circle, pi squared, the height, and then because it's a cone, we divide by 3. At what rate is the height of the water, h, changing when h equals 0.5? So, first step, we write down our equation. Well, this time they just gave it to us. The volume is 1/3 pi r squared h. We're looking for the rate, the height of the water is changing. At what rate? So we're looking for dh over dt. Alright. Step 2, take the derivative of both sides. So derivative of v is 1. By implicit differentiation or chain rule is 1 times dv over dt. Equals 1/3. Pi is a constant. Okay. Now we have a problem. Well, it's not a problem, but we can differentiate this, but then we would have to use the product rule. There's a simpler way of doing this. We should just recognize that, hey, from the diagram, we see that when the radius is 1, the height is 2, and they're directly proportional. These are similar triangles. Therefore, we see that the radius is height over 2. So we can just replace the r squared, r and r squared, replace that with height over 2 squared h. Okay. So actually I should do that up here. So I'm going to erase the r with h over 2 squared. Okay. And that's equal to 1/3 pi 1/4 from the 1/2 squared h cubed. Okay. So when we take the derivative, 1/3 is still there, pi is still there. There's another 1/4 term. And then the derivative of x cubed is 3x squared times dx over dt from the implicit differentiation, from the chain rule. Okay? Okay. Step 3, plug in. We know that dv over dt is 0.02. We know that h is 0.5. So 0.02 is equal to 1/3 pi 1/4 times 3 times 0.5 squared times dx over dt. Okay. The 3 and the 1/3 here cancel each other out. These cancel. So we finish the algebra, so we get 0.02 over pi equals, we have 1/4, and here's 0.5 squared, which is 1/2 squared, which is also 1/4. So all of this is 1/16 times dx over dt. Multiply both sides by 16, so we know that dx over dt is 16 times 0.02 over pi. 16 times 0.02 is 0.32. So all of this is equal to 0.32 over pi. So that's the rate at which height is changing. Okay. If we pay more attention, the height is actually decreasing. So if we're being rigorous, we can recognize that dx over dt is actually has been negative because dv over dt has been negative. Okay, because the height is decreasing. So that's it for this example. Okay. One more example. Here's an example from science: energy and motion of molecules. So, for example, here's a gas. Like all matter, like gases, liquids, solids, are made of molecules. So here's a gas. Here's a gas of oxygen molecules. Oxygen is O2. Each molecule has 2 oxygen atoms. When it gets warmer, see the temperature is increasing. It's getting less and less negative. The molecules move faster and faster. So really, temperature is just a measure of how fast the molecules are moving. And when it gets colder, the molecules move slower. This is negative. There's another temperature scale, kelvins. Kelvins is just really Celsius plus about 273. That's what Kelvin is. Okay. Different scale. 0 is the lowest possible temperature. 0 Kelvin is the lowest possible temperature. At 0 degrees Kelvin, the molecules stop moving. So here's the problem. The temperature of a gas is related to the root mean square velocity. It's kind of the average velocity because these molecules, some are moving faster, some are moving slower. We need an average of the molecules in the gas by the following equation. V is equal to the square root of 3RT over M. R is a constant. It's about 8.314 for the units we're in use. Big M is molar mass, which is 16 for oxygen. It's about 16 for oxygen. At room temperature, which is 15 degrees Celsius or 288 degrees Kelvin, we're going to need to use the kelvins for this problem. If the temperature is increasing at a rate of 1 Kelvin per second, so in other words, d big T for temperature, over d little t for time is 1. At what rate is the velocity of the molecules increasing? So we want to know dv over dt. Okay. All right. So step 1, as usual, we write our formula. So v is square root of 3RT over m. Square root means to the 1/2 power. That's what square root means. For our problem, r and m are both constants. They don't change. R is 8.314, M is 16. So we can pull that out. So it's 3R over M to the 1/2 power. And then we have big T for temperature to the 1/2 power. Okay. Now we can take our derivative, step 2, take the derivative of both sides. So the derivative of V is 1 times dV over dt, little t for time, equals our constant, 3R over M to the 1/2 power, times the derivative of t to the 1/2 power. By the power rule, that's 1/2 big T to the negative 1/2 power. Okay. Let me make our handwriting a little bit better. That should be an R. Okay. Step 3, we plug in numbers that we know. We're looking for dV over dt is over here. All right. So we have 3. R, we're told is 16. Oh, sorry. R is not 16. M is 16. R is about 8.314. So 3 times R, 8.314 over 16 to the 1/2 power. Oh, sorry. So when I took the derivative of t, I forgot to do the chain rule. So it's d big T over d little t times the rate of change of temperature. Okay. Next, we have times 1/2. And then big T, we're told is about 288 because we need to use kelvins for this. And then d big T over d little t is 1, as we're told. So the rest we can use a calculator. If we use a calculator, we do 3 times 8.314 divided by 16. And then take the square root of that because that's the square root is the same as to the 1/2 power. Divide by 2 times 288. And I get about 170, 180. So what does that mean? That means that when the temperature is going up at a rate of 1 degree per second, on average, the molecules are going faster by 180 meters per second. That's a lot. Yeah. Okay. If we go back to our simulation, we see that the molecule is actually moving really fast when the temperature is, yeah, it's actually moving really fast. All right. That's it for this video.